Hello everyone, my name is Abdullah, and today I'll be presenting my solution for task 1 of the assignment 5. And the objective of this task was to develop an AI model using TensorFlow and OpenCV that can recognize uh, 43 different types of row signs from the GTA's RB dataset. This kind of system is an essential part of computer vision in self-driving cars. And data loading, so load data function, let's begin with it. In my implementation, I looked through all 43 folders inside the GT ASRB SRB directory, and where each folder corresponds to a specific traffic sign category. To make sure the code works across different operating systems, I used OS path join here, and 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 for hand so it runs correctly on both Windows and Mac OS, for example. And within this loop, yeah, I used OpenCV CV CV to resize. This ensures that every input has the same size, which is required by the image width and image height constants, and is necessary for training neural network. And so let's move on to the get model function, where I build the convolutional neural network, CNN. So the model takes input images of shape, for example here, 30 by 30 and 3, and representing our RGB images. The architecture includes two convolutional layers. The first layer has 32 layers, and the second has 64 filters. Yes, and both use 3 by 3 kernels and their ReLU activation function. And each convolutional layer is followed by a max pooling layer. Max pooling layer with a 2 by 2 window, which helps reduce the spatial size and focuses on the most important features. After that, the data is flattened and passed into a fully connected dense layer with 128 neurons. And to reduce overfitting, I added a dropout layer with a rate of 0.5. And finally, the output layers contains 43 neurons, one for each class, and it uses the softmax activation function to perform multi-class classification. So here in README MD, I described the experiments I conducted. So at first, I tested every simple model with just one convolutional layer, but it performed poorly, achieving only 5% accuracy. So after adding a second convolutional layer and turning the dropout parameter, the model improved significantly. This in recognize more complex patterns. Here we can say it in our output. So in the final version, the model reached over 93% accuracy on the test data, which is strong result for this task. And that's the end of my explanation of first task. Let's go to the second task. Yeah, in the second task, the goal of this task was to build an AI system that can analyze English sentences, determine their grammatical structure, and specifically extract noun phrase chunks. This is an important concept in NLP, as it helps machines understand sentence meaning and identifying key subjects. So for this task, I used the NLTK library along with context-free grammar, or CFG. Now, wait. So first, I implemented the preprocess function. It takes a raw sentence as input and converts all characters to lowercase. Then I used NLTK's word tokenize function to break the sentence into individual words. To clean the data, I filtered out any tokens that do not contain at least one alphabetic character. This removes punctuation, marks like commas or periods, ensuring that only meaningful words remain. And so the most complex part of this task was defining the grammar rules in the non-terminals section. The grammar begins with the start symbol S and is designed to handle both simple sentences and more complex ones connected with conjunctions, such as Holmes sat down and lit his pipe. For noun phrases or NP, I created rules that include determinants, adjectives, and prepositional phrases. So one important feature is the recursive adjective phrase rule, which allows the model to process multiple adjectives in a row. For example, a little moist red paint, without needing separate rules. So I aim it to balance the grammar so it could successfully parse all required sentence while avoiding overly broad or incorrect structures. And in NP chunk, noun phrase chunking. Next, so in this task, a noun phrase chunk is defined as an NP that does not contain any smaller NP inside it. My implementation goes through all subtrees of the parsed sentence. It selects those labeled as NP and checks whether they contain any tested NP nodes. So if no such nested structure exists, the phrase is considered a valid chunk. For example, in the sentence, the armchair in the home, the function would return the home because it is the simplest noun phrase without any internal NP. So summary of this result. In conclusion, the parser is able to correctly process all sentences provided in the dataset. From short ones like Holmes sat to longer and the more descriptive examples. This demonstrates how a well-designed grammar can effectively represent a human language in a structured machine readable way. So thank you for your attention. Goodbye.